The universe was born 13.8 billion years ago, and within its first second gravity, particles, mass, and space all came into existence. What began as something unimaginably small has grown into an immense cosmic realm filled with superclusters of galaxies stretched across dark, web-like filaments. These structures are separated by such enormous distances that even the fastest thing in existence would need millions of years to cross them. As we learn more about how the universe began, we have also started wondering how it might end. Will it eventually lose all life, stars, and galaxies? Could it collapse, freeze, or even disappear entirely? No one knows for certain, but with modern technology we are beginning to understand the forces that shape the universe, and the possible endings are as unsettling as they are fascinating. To predict the far future of the universe, we must understand how space-time expands, how galaxies move, and what causes these behaviors. The universe is not expanding like a bubble pushing outward from a center. Instead, every point in space stretches equally, from the space between you and your screen to the most distant galaxies. The more space expands, the more room there is for further expansion, which accelerates the process over time. This is similar to a balloon inflating while we stand on its surface. No matter where we stand, the surface grows at the same rate, and the center seems to be everywhere. This expansion is weak on small scales, so gravity can hold things like planets, stars, and galaxies together. But beyond our local group of galaxies, objects drift away from us, something we observe through redshift, where light stretches into longer, redder wavelengths. The current rate of expansion is estimated at about 68 kilometers per second per megaparsec. That means for every 3.3 million light-years, the expansion pushes space outward at that speed, and farther regions are pushed even faster. Eventually, galaxies far enough away move away faster than light can travel, not because they break the speed limit, but because the space between us grows faster than light can cross it. This creates a cosmic event horizon, a boundary beyond which light will never reach us. Once galaxies pass this horizon, they are lost to us forever, cut off from communication and observation. More than 95% of the galaxies we can currently see have already crossed this point and are disappearing from our reach. The force behind this behavior is something we call dark energy. The name sounds mysterious, but it simply represents our lack of understanding. We know it drives the acceleration of cosmic expansion, but its true nature remains unknown. Unlike normal matter, dark energy seems to maintain a constant density even as the universe grows, meaning more of it appears as space expands. We discovered its effects in 1998 when studies of distant supernovae revealed that expansion was speeding up, not slowing down. That discovery marked the moment when the universe entered a new era dominated by dark energy, around 9.8 billion years after the Big Bang. With these ideas in mind, we can imagine the universe's distant future. In a few billion years, the Milky Way will collide and merge with the Andromeda Galaxy, forming an enormous new galaxy. Smaller nearby galaxies will eventually join it as well. Everything beyond our local group was pushed too far away in the earliest moments of time, and gravity will never pull them back. As dark energy keeps stretching space, even the nearest galaxies will slip beyond the cosmic horizon. In about 150 billion years, everything outside our local supercluster will vanish from view. The universe will appear empty beyond the boundaries of this merged galaxy, and any future intelligent beings born in this era will never know that countless other galaxies once existed. As the universe expands, practical consequences appear. New galaxies will no longer form, and existing galaxies will slowly die. Star formation will cease, and current stars will eventually collapse into white dwarfs, neutron stars, or fade away entirely. One by one, the lights of the universe will go out. Around 100 trillion years from now, the final red dwarfs and white dwarfs will exhaust their fuel and fade into dark, cold remnants. The universe will enter a second dark age, lasting far longer than the first. The faint glow of the cosmic microwave background will dim beyond detection. Only supermassive black holes will remain, slowly consuming whatever matter is left. After an astonishingly long time, even these black holes will evaporate through Hawking radiation, eventually disappearing. The universe will become a cold, empty void, unimaginably vast and nearly featureless. Scientists have suggested several possible ultimate fates. One idea is the Big Crunch, where gravity eventually stops expansion and reverses it, causing the universe to collapse back into a dense state. This would heat everything until even atoms break apart, and all matter could merge into one colossal black hole before collapsing into a singularity. Some imagine that such a collapse could trigger another Big Bang, creating a new universe. Another possibility is the Big Freeze, where the universe continues expanding forever. As energy spreads out thinner and thinner, temperatures drop toward absolute zero. Entropy reaches a maximum, and no processes can occur anymore. Everything becomes still, cold, and lifeless. Another possibility is the Big Rip, where dark energy grows stronger over time. If its density increases, it could eventually overwhelm gravity not only between galaxies but also within galaxies, solar systems, planets, and even atoms, tearing everything apart down to the smallest particles. Space-time itself could rip apart. There is also the possibility of the Big Change, tied to an idea called vacuum decay. The Higgs field, which gives particles their mass, might not be in a truly stable energy state. If a quantum event triggered it to drop into a lower energy state, it could release immense energy, creating a bubble of true vacuum that expands at the speed of light. Anything inside that bubble would be destroyed instantly, and the laws of physics would change in ways that prevent atoms and molecules from forming. Such a bubble could appear anywhere, at any time, and we would never see it coming. Fortunately, because most of the universe is disconnected from us by the cosmic expansion, the chance of such a bubble forming inside our local group is extremely low. These four scenarios, the Big Crunch, Big Freeze, Big Rip, and Big Change, outline the possible ends of our universe. The Big Freeze seems most likely based on current evidence, but we cannot rule out other forms or new physics entirely. Our desire to understand the universe's ultimate fate comes from our deeper search for meaning and our place within it. Life may persist long after us, perhaps in forms or places we cannot imagine. Humanity has existed for only a brief moment compared to cosmic time, yet in just a few thousand years we have uncovered extraordinary knowledge about the universe. If we survive far longer, we might one day observe the forces shaping the universe's destiny firsthand rather than relying only on equations and predictions. Until then, all we can do is continue exploring, learning, and appreciating the incredible fact that we exist at all within this vast and mysterious cosmos.